Hello everyone, my name is E-Hassin. I'm a student at North University. Today I'll be talking about my project entitled NeuroSpy, a low-cost portable IoT-enabled EEG and ECG data processor, which I have been doing for my academic purposes. The contents of the presentation include motivation, system design, result analysis, cost analysis, and finally the key findings, which will conclude the presentation. In the next couple of minutes, I will give you a brief introduction to my project. I'll describe the goals and also talk about how people will benefit from it. So let's get started. In this modern world, everybody uses different kinds of gadgets to fulfill different needs. How about medical devices to stay in touch with our bodies? Biomedical devices are expensive as they are complicated in design. The main purpose of this presentation is to introduce you to a multifunctional portable biomedical device which can monitor the user's brain activity, heart rate, and ambient body temperature simultaneously in real time. Our goal is to design such a biomedical device at a minimal cost. As I said earlier, currently available commercial devices are good, but the problem is they are expensive, especially brainwave monitoring devices. Users have to pay monthly subscription fees to use those devices. On the other hand, our objective is to feature a similar device at a low cost. Most of the commercial devices offer single functionality based products, but we are offering an IoT enabled multiple functionality based product which is safe, obviously battery powered, and most importantly, users don't have to pay any extra money for subscription purposes. As I said before, it's cheaper than other commercial devices, so more consumers can afford it easily. Industrial sectors like BCI, quadriplegia patients will benefit from this device. It suits best for developing countries. In this section, I am going to talk about the methodology, main features, system design and implementation process. An electric potential is developed in the neurons, and the combined potential from multiple neurons can be measured from different places of the scalp. An electroencephalogram measures the brain's electrical activity by placing EEG probes on the scalp. The intensity of brain waves changes subject to user's internal state. Electrocardiography, as known as ECG, is based on the technique of measuring the dissimilarity in blood volume in tissues. A subject's finger is illuminated by an infrared light emitting diode. More or less, the light is observed depending on the tissue blood volume. Consequently, the reflected light intensity varies with the pulsing of the blood with the heartbeat. A plot of this variation against time is referred to as a PPG signal. As discussed earlier, our device can monitor EEG signals, heart rate, and ambient body temperature in real time. NeuroSpy is the code name of our biomedical device. Usually, biomedical signals are too small, microvolts to be precise. We have to amplify it because our microcontroller cannot handle such a low signal. According to design, we have used a general-purpose instrumentation amplifier chip like AD620AN. In this primary stage, the gain is 100. After that, multiple signals of amplification are required to amplify the signal. We have used additional two separate stages of amplification. Gain in each stage is 100. We have used a 0.7 Hz high-pass filter and a 100 Hz low-pass filter in each amplifier stage to reduce unwanted noise. Additionally, a notch filter of 50 Hz is placed before the final output to get a clean signal. After that, the signal will pass through an analog to digital converter to get a digital representation of the analog signal. The FFT engine of the CPU will split the original signal into different frequencies. The sampling rate of our FFT engine is 64 samples per second. According to design, we collect ECG impulses through an infrared LED and a photodiode. The received signal is in millivolt stage, so we need amplification. We followed a multi-staged amplifier design, which is similar to our EEG unit. The total gain of the section is 1000. We have used a 0.7 Hz high-pass filter and a 2.84 Hz low-pass filter in each stage to get clean amplified signal. After this stage, the ADC will take care of it. It's a modular design. In this design, we have used a total of 4 8-bit microcontrollers to get the job done. Each microcontroller is interconnected through the I2C databus so that they can communicate with each other when needed. There is an EEPROM chip used in this design to store MySQL database credentials and other system-level configurations. It's IoT enabled. This unit is equipped with an Ethernet controller, so it can be used as MySQL client. That's why we can store biomedical related data into a central database in real time. We have used open source Arduino architecture to prepare its firmware. Here you will see the main logic board of the system. The physical image is on the left and the CAD representation is on the right. This is our final prototype. It's battery powered, that's why it's completely safe to use with the human body. There are 3 types of EEG electrodes available in market: dry, semi-dry and wet electrodes. We have used the wet type general purpose silver chloride based sticky type electrodes because the noise rate in wet electrodes is comparatively less than other types. Any ordinary silver chloride type sticky pads will work fine. These are easily available in almost every medical store. In this section, we will talk about result analysis based on different case studies. First, we have placed EEG probes on the right side of the frontal partial lobe, denoted as FP2, to detect eye blinks in real time. It is marked with red circle in the figure on the upper left. The figure on the lower left shows that the prominent peak frequency before eye blink was 29 Hz, which denotes the high beta region. The prominent frequency started to decrease while the eye closed. At the time, the region changed to the alpha band. After that, the region changed to the beta region again, with a peak frequency of 23 Hz. The same representation is on the right, which we have got from an oscilloscope during the eye blink test. This system can detect brain signals during a deep thinking state. To perform this kind of test, the user had to sit in a quiet and relatively dark place. Then he needs to try to relax the body and think about something profoundly for a while. To make 2 different states, we had to close both eyes, and after a while, we had to keep open both eyes while thinking. This figure represents the power spectral densities of the EEG waves during the performed thinking related tests. EEG data from the FP2 position of the human scalp are simultaneously recorded with our design device and a commercial device from Emotive Insight. Both of the devices returned almost visually similar results as well, which has been demonstrated in figures. The left graph represents the raw signal we have got from Emotive Insight, a commercial EEG monitoring device, and the graph on the right represents the raw signal from our custom device. We will see the actual representation of ECG signal recorded through an oscilloscope, which seems promising. Our system can calculate the pulse rate from 42 to 170 beats per minute. In this section, we will talk about the cost comparison between commercially available different devices and our device. Here, you will find the cost comparison with commercial vendors. We have collected those price tags from publicly available different websites. Our prototype is far cheaper than those. As I said earlier, no subscription is required in our prototype. It's also far cheaper than other devices. In this section, I will talk about key findings. Right now, it's the initial release of our system. To make it simple, we have used all through-hole components. We will try to make it more portable by using assembly components, more optimized and energy efficient in the future as well. The primary objective of this project is to build such a medical data analyzer that features similar to the commercial EEG devices at a minimal cost. We have performed several tests of our designed system NeuroSpy. The design data processor system shows almost similar results to other commercially available systems from different vendors. Our system is cost effective than the other commercial EEG data processors, with a reduction in the implementation cost of 2.22 to 90 times. So, this prototype can serve different purposes in developing countries with endless possibilities. Here is the list of references where we have got tons of knowledge during the making of this prototype. That's all, folks. If you have any question, I'll be happy to answer those. Thank you all.